Okay, ladies and gentlemen, welcome to our colloquium Quantum Contextuality in Quantum Mechanics and Beyond, QCQMB. It's my great pleasure to announce our speaker today. It's Ernesto Galvão of the International Iberian Nanotechnology Laboratory in Portugal, and also the Federal Fluminense University in Brazil. And today he will present a talk on the inequalities bounding non-contextual, local, and coherence-free models. Ernesto?
Thank you, Etiba. It's a pleasure to be here. Thank you for the invitation. So this is based on ongoing work with Rui Soares Barbosa and Rafael Wagner, who are also here at INL, where I spend most of my time. I'm on leave from Universidade Federal Fluminense. So this is the outline of what I'd like to talk about. I'll talk about an operational description of a very general type for a set of probabilistic processes and the correlations that arise. And then we'll look at Bell-Bull conditions of possible experience for those processes, which are basically logical constraints on the results that you can observe. Then we interpret those as coherence-free inequalities, so inequalities that tell you you are using quantum coherent states. And we interpret those inequalities also as non-contextuality inequalities, and that's why I'm talking in this colloquium series, right? Then I'll present many examples of small graphs and how to analyze them, and talk about some open problems. So that's the plan. So let's look at it's an operational description of a set of probabilistic processes of random variables that you're observing, okay? So I'll have a graph, as so often happens in these contextuality setups, but this is a more general I'll be using to describe other things, where the vertices are these probabilistic processes, and they output outcomes from some alphabet, okay? I'll assume nothing about the dimensionality of the alphabet of these outcomes. So each vertex Vi yields outcome OIK with some probability PIK, okay? And besides the processes themselves, which are represented by these vertices, we have also these edges, okay, forming the graph. And the edges are simply the probability that the two vertices yield the same outcomes, okay? So you can imagine these vertices yielding outcomes according to some probabilistic processes, and then you're looking at the probability that the outcomes are the same. This is basically a measure of correlation between them. And these edge weights for this weighted graph, these R's, are just a probability that the two outcomes are the same, okay? So this is a very general association between different processes and their correlations, right? Now, the first thing that we need to understand is that not all, my screen is not showing completely, right? So I have to do something about this, sorry. Let me see. I'll get out of full screen because it's not showing the, just a moment. Let me see what I can do here. Now, okay, so this is not ideal, but let me see. You can see my whole slide at least, right? Okay, so I hope you can see it now. Can anyone confirm that you can see?
Yes, it's just fine.
Okay, cool. So what I was saying is that this very general description of many processes, okay, not all edge weights are possible. So what I'm saying is, if you have a certain set of processes, you cannot observe all possible correlations between them. You cannot observe these probabilities that they are equal, cannot reach all the possible values that you might imagine. And this is exactly what's behind what George Bell, and Pitofsky looked at a long time ago, and that Boole called conditions of possible experience, right? And you can see this is a very nice reference where Pitofsky analyzes this and describes Bell inequalities in terms of those, right? So let's have a look at this graph, a general graph. The first thing to observe is that if you have a tree is a graph that doesn't have any cycles, okay? Then you don't have any constraints on the edge weights. So the conditions of possible experience are free for all, right? Because only when you have cycles, then you can have some contradiction about the different assignments that you made that makes something impossible, that bring a constraint, right? So what we're gonna do, which is have a look at the simplest scenarios that impose constraints, and the simplest scenario has to be a cycle, right? And the smallest cycle you can have is a three vertex cycle, and that's what we want to look at now. So if you look at the tree cycle, imagine A, B, and C are these processes, and these numbers, the edge weights, they're just the probabilities that the processes give the same results. So you can represent a general description of the edge weights with just this triple of numbers, okay, the three edge weights, where each number is this probability that the pair of processes that are linked by it give the same outcome. Then it's easy to see that some tuples, some triples like this, they are impossible because of transitivity of equality. So what this first vertex would be saying, right? It's saying the A equals B, A equals C, but B and C are different, and we know that can't happen, right? So this vertex, I'm sorry, this set of edge weights, they're deterministic, only 0, 1, is impossible by transitivity of equality, because if these first two entries are 1, the third one should be 1 as well, right? And this is not what it's saying. So of course, these three different vertices are not allowed, which means that the allowed vertices are only these 5 ones, which are deterministic vertex, deterministic edge assignments, right? And if you allow for convex combinations of these different possibilities, right, which are all okay. For example, this one corresponds to three states, three processes that always output different outcomes, right? And these are always output the same, and these are pairwise equal. So if you look at the convex combination of those, it's the convex combinations of these green points, and it forms a polytope in general. It's a polyhedron in this three-dimensional space. And this is what is allowed. These are the conditions of possible existence for this very simple setting, okay? We see there are some vertices which are not allowed. That is the red ones, okay? Because they violate this transitivity of equality. So if you look at this object, okay, we have described it in terms of vertices. It's just a polyhedron. But of course, you can describe it in terms of facets. And these are the facet inequalities. There are 3 of them, which are non-trivial, corresponding to exactly these 1 per deterministic vertex that you forbid, right? That you made impossible. And these are exactly the inequalities. And we've completely characterized this very simple scenario. Now, of course, I want to go back to quantum mechanics, because everything that I did here is completely logic. That's it, as described by Boole, okay, in the 19th century. But now I want to put some quantum flash onto this, right? And the way to do this, one way to do this, is to look at the two-state overlap, okay? The two-state overlap is this quantity. It's just a modulus squared of an inner product of 2 states. If you have mixed states, this is a generalization. It's just a trace of the product of the density matrices. And it has a very clear operational interpretation, because it's a probability of preparing state A and projecting onto B, or vice versa, of course. Interestingly, this overlap can be estimated without knowing anything specific about psi and phi, about 2 different states, right, or A and B here. And you can do that using the swap test. So you just input the states here, you do Hadamard, the control swap gate, and the Hadamard, and when you measure the top qubit here, you get an estimate of the overlap, right? So this is very useful in many quantum information tasks, and it can be used to estimate this quantity, which is a completely relational quantity. It has to do with the orientation of these two states, something like a cosine squared of this angle between them. So now what I'm going to do with these overlaps is to have a look at the graph scenarios that I just described and parameterize any graph scenario which is logically possible, consistent with these conditions of possible existence, using coherence-free quantum states. So coherence-free quantum states, they are classical states, okay? And we'll have a look at, of course, violations of those as well, right? So we're coming from logic, we're going to classical world, and then we'll go and find the quantum predictions violating these classical expectations. So the PDF didn't work so well, but you can read this. What are these classical states? Okay, what I'm calling classical states are diagonal incoherent mixtures of states in a fixed reference spaces. So the classical world has a reference basis, a reference observable that you can measure, and that's the only observable, okay? So you have no superpositions because you're not allowed this set of classical states. So the global density matrix describing the whole system is diagonal in these reference spaces. Each local system, you can have to take the partial trace, is also diagonal. And the overlap between two different classical states is just the probability of getting equal outcomes of the reference observable, okay? So here, if we get rho and sigma, this is just the brackets, okay, for the matrices. You have two density matrices of three-dimensional systems which are diagonal, okay? So if you take the overlap between these two, you just have to take the trace of the product of them, and this is the sum, okay, of the product of the diagonal elements. But the product of the diagonal elements is just this probability rho 1 times sigma 1 plus rho 2 sigma 2 plus rho 3 sigma 3. It's just a probability that you get equal outcomes, okay, either the first, the second, or the third. So for coherence-free states, which are diagonal, all diagonal, the overlap has this very simple interpretation. Is the probability of getting the equal outcomes when you measure the reference observable, okay, which is the only one that exists in this classical world. So you can look at this as just a quantum way of parameterizing a general joint probability distribution function of measurement outcomes, okay? You could have talked just about the probability of different outcomes instead of talking about these diagonal elements. It's the same thing. But by introducing these quantum states to parameterize these classical distributions, you allow the possibility of going beyond this set and looking at states which are not diagonal, okay, which have coherences. And that's what we're going to be doing in a bit, okay? So now we can use overlaps and give an interpretation for the classicality inequalities, the Bell-Bull inequalities that we found, okay? Now, each vertex in a graph, I'm taking the triangle as an example, gives you the outcomes of a certain basis measurements or reference basis measurements on a quantum state, okay? So here I'm giving the quantum state. You're going to take the quantum state in each vertex and just measure in the classical diagonal reference spaces, and this gives you outcomes with some probabilities. The edges are the probabilities that these outcomes give the same result. So it's exactly the same interpretation as we had before. It's just that now I'm parameterizing the probabilities from a joint quantum state, right? Which must be diagonal for classical states. Now, for coherence-free, for these classical states that I've just defined, we can measure these edge weights exactly as I told you before. You measure the local observable on A, measure local observable on B. They are a diagonal in the same basis. And the overlap is going to be the probability that the outcomes are the same. So this is one way of measuring. But there is another way of measuring the same quantity, which is an indirect measurement that uses a swap test, okay? So you can take row A and row B, which are diagonal and classical. You feed into the swap test circuit, and you obtain an estimate for the overlap, okay? And these two quantities, these are just two different ways of measuring the same thing, okay? It gives you the probability of getting the same results if you measure the reference observable on each system. Now, what I described to you is that you have these possibilities, okay? So if you're dealing with coherence-free states, you will be limited to measuring overlap triples inside this polyhedron, okay? But of course, if you have states which are not diagonal in the same basis, for example, these three states separated by 60 degrees on a great circle, the Bloch sphere, and you measure their overlaps, which is something that you can do, right? You obtain three quantities which violate the classical expectations that we had. See, the classical expectations are that you should be inside this polytope, and you're finding, and you find this other body, the quantum body, which is an inflated version of this polytope with new bulky areas, you know, volumes outside of this polytope. And if you measure the three overlaps using the swap test and obtain a red point like this one outside of the classical polyhedron, this is a sign that these states have coherences. And this is a sign that they have coherences which is independent of the basis, okay? You're just saying there is no way this statistics is consistent with three states which are simultaneous and diagonalizable independently of the basis, okay? So this appeared in this paper that I did together with Daniel Brod in theory. And this was done in an experiment in which I collaborated as well recently using photonic states. So they basically created photonic states with states like these, measured the overlaps between pairs of states, and you obtain these states. So just from the overlap measurements, you know that these states cannot be diagonal in the same basis. So these measurements work as a basis-independent coherence witness based on overlap measurements, which are these relational quantities, only have to do with how one state is related with the other. You don't reconstruct the states. You just go for this three quantities which are of interest. Okay. Now I'd like to go back to the graph scenario that we had a look. And interpret it, okay, as contextuality inequalities. So we've interpreted the inequalities that we found, these Bell-Boole inequalities, as coherence witnesses, okay? Now I'm gonna give you a different interpretation for it. So now again, we have the same interpretation for these vertices, okay? And now I want to look more closely at the global probability distribution function, okay? Because a classical model, the way I described to you, it's a distribution over the possible states that you can have that you're measuring using the reference observable. And these states are all classical. The convex combinations are classical too. So you can compute the probability of getting equal outcomes, that is the weights of this graph. And the weights must satisfy those Bell-Boole inequalities, which are the edge weights that we had here. Okay. So we saw that a quantum realization of this classical model, okay, can be done with the diagonal density matrices that are diagonal on a fixed basis, and the reference observables just reveal pre-existing properties in this case, right? But pay attention to these words, okay? This classical model has a global probability distribution function over the classical states, and hence it's a classical non-contextual model, because the existence of a global PDF is equivalent to non-contextuality by Fine and the Brandenburger theorem, right? So this quantum realization with diagonal states is just a way of parameterizing a general non-contextual model. Okay, so if you look at these, just at the behaviors, the probabilities of the outcomes that are coming, you're just parameterizing the states that you're preparing with diagonal states, and the observables you're measuring corresponding to each vertex is just a reference observable. You're parameterizing them with quantum states, right? So you always get non-contextual hidden variables, and you have a global probability distribution that that describes them, which is exactly the probabilistic weights of any distribution inside that polytope that I just described. So this means if you have violation of these expectations, okay, this violation of these expectations are revealing contextuality or non-locality, depending on how you interpret which measurements correspond to these vertices. Okay, and this is something we'll see in many examples that I would like to go to now. Okay. I mentioned I just worked out with you the triangle case, right? But you have this classicality inequalities, Bell-Bull inequalities for the k-cycle scenario, where you have k vertices, okay, linked in a big cycle. And these are the inequalities, okay, that you have. And we found these inequalities looking at these coherence-free, these coherence witnesses. But of course, this is very old. This was actually found by Boole a long time ago. And it appears in the work of Hardy and Abramsky on logical Bell inequalities and on the characterization of all the cycle inequalities that appears in this other paper here. If you're interested not just in the big cycle, but you're interested in a general graph, and you would like to know what are the constraints, okay, Bell-Bull constraints for a general graph, you can computationally find the facets of the corresponding classical polytope. One way to do it is to just consider all possible deterministic 0-1 assignments for the overlaps, okay, or the edge weights, okay, R's. Now you delete all the tuples which are forbidden by transitivity of equality. An example was that triple 1, 1, 0 for the triangle. That was impossible. You have to look at each of these deterministic ones, eliminate the red ones, the impossible ones, and the remaining ones are the classical ones that are allowed, and any convex combination of them is also allowed, right? And if you have a violet, and then you can find the facets corresponding, describing this polytope, and the violation of these inequalities, of the facet inequalities, is a witness of coherence, contextuality, or non-locality, depending on how you chose the observables to describe these different vertices you have. So now some examples, okay? Because this was all very theoretical, let's look at a simpler example that is more related to things that you probably know. So take a 4-cycle, okay? You have 4 vertices. Each vertex corresponds to outcomes of some experiments, okay? So, and we assume that these outcomes are dichotomic, just plus or minus 1, okay? So then this edge weight is just a probability that these two measurements, A1 and B1, give the same result, the probability that they are the same. Of course, if you have dichotomic measurements and you know the probability of them being the same, then you know everything there is to know about the correlation, and you can actually write the expectation value of these two observables in terms of the edge weight or vice versa, right? Using this equation. Now you look at the cycle inequalities, right, that I described here. If you look at the cycle inequality for 4 overlaps in a cycle, 4 edge weights in a cycle, this is the cycle inequality that you have. They're all of this shape, okay? 3 of them minus the 4th, smaller than or equal to 2. And if you translate using this to expectation values, you just get the CHSH inequality, okay? So the 4-cycle inequality, if you interpret these as local measurements of Alice and Bob, and they are dichotomic, corresponds to the CHSH inequality. If you look at the 5-cycle, okay, you have the same kind of shape, but now 5 vertices in a cycle. You do the same mapping. You assume that the outcomes are dichotomic. You look at the cycle inequality for a 5-cycle. It's just this one, and it translates exactly to this inequality in terms of expectation values. And this inequality is the KCBS inequality, Classical et al., which was found in 2008. So this is another inequality, which are Bell-Bull inequality for this scenario that translates as a non-contextuality inequality. You can also look at the simplest scenario with constraints, okay, the 3-cycle scenario, but it's a bit more involved because the 3-cycle doesn't appear directly in an easy way in quantum mechanics. What you can look at is a scenario that kind of doubles this triangle. So you have 3 settings for Alice, 3 settings for Bob, but you guarantee that the first setting of Alice is completely aligned with the first setting of Bob, and also for the second and the third. which means if you use a maximum entangled state, you always get the same outcome, right? If you measure at Alice and at Bob along the same direction. So if you look at the scenario and you impose that these probabilistic processes are always giving the same outcomes, they are actually identified. So you kind of collapse this structure into the simpler structure, okay? And the classical inequalities that were present here become the classical inequalities of the triangle, and which translate to the original Bell inequality for 3 settings and perfect correlated outcomes when you have the same setting at both parties, okay? And I think that there could be a wrong sign here. So sorry about that, but well, I can try to fix it for the version that I'll share, okay? But of course, now you can look at more general graphs, right? And which are not cycles. So we looked at the simplest graphs, which were not cycles. And this is the simplest one, which gives you different inequalities, okay? Which are quite interesting to look at. So this is also has 4, this graph has 4 vertices, but now they're all connected. So it's a complete graph on 4 vertices, K4. And all the inequalities that appear here, they are 3 cycle inequalities, 4 cycle inequality that appears, but you also have this new one, which is different. And it's exactly this inequality that I'm writing here and color coding, okay? The overlaps connected to a single edge have a coefficients 1, and the overlaps connecting the remaining vertices have red color. They have a -1 coefficient, okay? And I have 1 on the right hand side here. If you want to realize this using states on each vertex and overlap measurements, like we did in the first interpretation of this graph, you can pick these states here. They are Q-trig states. And the left-hand side for this inequality gives you 4/3, which of course is not smaller than 1. So this is a quantum violation of this Bell-Bull inequality, looking at it from the point of view of overlaps, just states and overlaps between states. But if you look at it from the point of view of contextuality and non-locality, right? Of course, we can go back to the CHSH scenario. And what you have here is a kind of different inequality, which relates the correlations you obtain, like we did previously with the 4 cycle inequality. But you also have 2 quantities, which are these cross terms, which have to do with the overlap between what Alice is measuring, the 2 settings of Alice, and the 2 settings of Bob, okay? And these are quantities which are just quantifying the incompatibility of these observables that Alice is measuring and the observables that Bob is measuring. So this single inequality is and putting bounds on the correlations between Alice and Bob, if you interpret it in terms of the CHSH scenario, together with the incompatibility of the measurements that Alice and Bob choose, okay? So this is just one proposition, one way of trying to interpret this inequality, okay? So this is ongoing work, of course. We're still thinking about the interpretation of this higher order, these larger graphs. Of course, we want to look at larger families, okay? And we actually managed to prove an infinite family of facets for Kn, for the complete graph on any number of vertices, which just generalizes this single inequality for the 4 vertex complete graph to any complete graph, okay, with more vertices. So the inequality is like this. You take the complete graph on n vertices. Here I drew the 5 vertex version. And then you identify, you give a +1 coefficient to all the edges that leave as 1 vertex in particular. And you give a -1 coefficient to all the edges connecting the remaining vertices, which are not the chosen one, okay? So this is the kind of inequality you have, a sum over greens minus a sum over reds, and the right-hand side is 1. And we managed to show that this is true. This is a facet of the classical polytope as you increase. But as you increase for any number of vertices, okay? But as you increase the number of vertices, more and more new types of facets appear. So this is one that appears already for the 4 vertex one. But when you go to 5, K5, you have many other facets. So it's interesting to look at the different types of facets that appears. For K5, we can still characterize completely the types of facets, but with K6, there are so many of them, it starts to become a bit unwieldy. So here are some facets from K5 that we found, which we found interesting. So this one is a pentagram. See, you have a pentagon, and you have with +1. So the edges in the green, the edges in green have a +1 coefficient. The edges in red have a -1 coefficient, and the right-hand side is 2. And you obtain this by doing, this enumeration of possible vertices, finding the facets, and these are facets that appear. And if you interpret this in terms of overlaps, you can just pick these 5 states to be the 5 states equally spaced in a regular pentagon on a great circle of the Bloch sphere, so a 2-dimensional qubit would do. And you calculate the overlaps associated with these 5 guys, and you find on the left-hand side 2.795, more or less, which is not smaller than 2, of course. So this is a violation. The other inequality, an interesting one that we found, see they all have some symmetries. It's nice to see. It's this other one, okay? You just have these 5 states. 3 of them are equally spaced in the great circle of Bloch sphere, separated by 120 degrees, and the other 2 are in the poles, okay? And if you look at this combination of this linear combination of the overlaps between these 5 states, you get 9/4, which is not smaller than 2, but 2 is the kind of classical bound for this inequality. And these inequalities, you can find them. You can use them to do this trick that I showed you with the 3 triangle, duplicating it to do a Bell scenario. You can do the same thing with these inequalities, and you duplicate them to do a scenario involving 5 measurements on each side, right? So this is one interpretation for these classicality inequalities, which is different from the coherence witnesses that they also mean, right? That you can also use them to characterize coherence between 5 states. So one interesting aspect of looking at these bigger and bigger graphs, right, was something that we realized by looking at the complete graph on n with n vertices, okay? So if you take a complete graph, this is just the K4. You can look at all the edges. So the 4 vertex complete graph has 6 edges. And now we're interested in looking at how many deterministic assignments there are for these weights, because this corresponds to the number of deterministic assignments for the edges that you have to consider, and then do the convex combinations of them to find the facets of the classical polytope, right? So the first thing you want to ask is how many are there, for you to have an idea of how complicated it's going to be to do this process of doing the convex combinations. And the interesting thing is that for the complete graph, you have a one-to-one mapping between assignments, these deterministic assignments, and equivalence relations between sets of vertices, okay? So I'll explain why, okay, via some examples. So if you just take this 4 vertex example, what could happen between deterministic assignments means the process that you're using are always outputting events which are always equal to some of the others, at least one, or are always different from all the others, right? So that's the meaning of having these 0-1 assignments for the different overlaps, for the different edges in the graph, okay? And if you look at this assignment in particular that I'm on the left, you have a 1 assignment for R1, R4, and R6, okay? Which means these 3 vertices in green are always outputting the same events. They're behaving identically, right? They are correlated, perfectly correlated. Whereas the 4th vertex, the 4th process, is always giving outputs which are different from these 3, right? So it's perfectly anti-correlated with these 3. So this means there's an equivalence relation between the green vertices, an equivalence relation, a singleton, right, of the fourth with itself, right? It's different from everybody else. So so having a deterministic assignment like this, which satisfies the Bell-Bull inequalities, okay, means identifying who is equal to whom and who is different from whom, and this is a complete is one way of doing of breaking the set of 4 vertices into an equivalence relations, right, given by equality. This is another way in which you identify just one pair of vertices which are the same, the green ones, and another pair of vertices which are the same, the blue ones, and all these other zeros are saying the blue ones are different from the green ones. So this is a different way of breaking the vertices into equivalence relations of equality sets, right? And these numbers are tabulated, of course. They're called Bell numbers or exponential numbers. You can check them on the Encyclopedia of Integer Sequences. And this is how the counting goes. Okay, there's a recurrence relation that you can use to count these, right? And the number increases, of course, very fast, exponentially fast, as you increase the number of edges. Okay. Sorry, this is the number of vertices. So of course, for this number of vertices, you have n times n minus 1 over 2 number of edges. Okay, so this is an interesting structure. And of course, you can look at these equivalence relations for incomplete graphs as well. And then you don't have as many constraints, because the complete graph is the one that has the most constraints, because you have all the cycles. Like here, you have this triangle, this other triangle. You have 4 triangles. You have a 4 cycle. And all of these, each of these cycles imposes constraints on deterministic assignments. So having the complete graph is the worst case scenario, right? You're restricting the most the classical states allow. So I hope I managed to show you that you can have a look at this initial graph that I presented to you in the beginning in different ways. You can look at it in terms of states and their overlaps. And you can look at it in terms of outcomes of measurements that you have. And the edges are just a probability that the outcomes are the same. And looking at these 2 different ways, you manage to define coherence witnesses, which are basis independent, and also find non-contextuality and locality constraints, right? But these inequalities that you obtain by looking at the classical polytope, they're quite general, okay? And the reason why is because this trace of row A, row B, or trace of 2 operators is a very general quantity, right? It's basically a probability in quantum mechanics. So looking at these classical models and the constraints they impose on probabilities is a very general thing. So for example, you can a more general encoding or a different way of looking at these graphs in terms of quantum mechanics is by looking at some of these vertices as states and some of these vertices as measurements, okay, projectors. So in this example, this is just a different way of looking at the SH scenario. You have the central vertex, which is the maximum entangled state you want to measure. And each of these other vertices around it is a joint projector that Alice and Bob jointly measure, okay? So you can think of this as a 4-dimensional projector. Sorry, a 1-dimensional projector, but defined on the 4-dimensional Hilbert space, right, of Alice and Bob. And then the orange edges, they're just probabilities, okay, of preparing state psi minus, the single state, and measuring onto one of these projectors, one of the 4 that you can measure. Whereas the blue edges, they are quantifying, for example, between here and here. The difference between these 2 is just the projector onto A, onto the state at Alice. So this is just a compatibility between the 2 settings that Alice has, right? And if you look at this graph and apply just the triangle inequalities for these 4 triangles, you see that these blue quantities cancel out. when you sum all the inequalities, you obtain exactly the such inequality that we had for the fourth cycle that we looked at before. And this has to do with this way of complementing a graph, right, to obtain another graph, extending a graph, right? So this different way, two different ways of looking at these classicality inequalities are interesting because they're connecting different resources. They're connecting very different things in quantum mechanics. One is about coherence, and the other is about contextuality and non-locality. So it's very interesting. We're just starting to explore the connections between the two. And it's interesting to see what are the zero-sum bounds, how much quantum mechanics violates. And we saw some examples for the inequalities of K5 to show equivalences between protocols that use coherence on one side and contextuality on the other, and to try to find unified resource theories for these two different types of resources, looking at them as a unified non-classicality concept. So I'm reaching the end of what I wanted to tell you. Just wanted to recall what we covered, right? We introduced basis-independent coherence witnesses based on overlaps. And then we went back a little bit and looked at the more general graph scenario describing this situation. And we saw that coherence-free states, they can be modeled by quantum states, which are diagonal in a single, they are obtained by quantum states which are diagonal in a single basis. And when you get states which are not diagonal in a single basis, then you can violate these expectations from the classical model. And these classical bounds, they're also bounds on contextuality for non-contextual theories and bounds for local theories. And we saw some examples, and there are others which I didn't include here, like the GZ inequality cycle, like these multi-setting inequalities of caves, and so on, right? So this is interesting because it's a single framework connecting contextuality and coherence. And so this is hopefully useful to look at quantum computation advantage in general and advantage in particular models and particular protocols. So there are many open problems, okay? One is a relationship. What's the relationship with the PBR theorem? Because the PBR theorem is about overlaps, and we are obtaining bounds on overlaps. So how can you connect the two things, right? Another, of course, I gave some steps here. I showed you some steps about how to find new Bell and non-contextuality inequalities and how to find the bounds, quantum bounds that are reachable. And a third open problem, which is a bit different, is the foundational importance of relational quantities, because the overlaps, they are relational, right? Because they only have to do with the relation between one state and the other. So if you apply a unitary to the two states, the overlap doesn't change. The most general type of invariants under unitaries are so-called Bargmann invariants, which have this shape here, okay? It's a product of, it's an inner product of states in a cycle. So here you go from A to B to C to A again, okay? So since overlaps proved to be so fruitful for looking at classicality from the point of view of coherence and from the point of view of non-contextuality, I'm sure that Bargmann invariants of this type are also a useful concept to quantify these quantities and quantify classicality. And we have a paper that I didn't mention, exactly looking at how Bargmann invariants of this type help you find and witness complex valued amplitudes in quantum mechanics, for example, witness coherence like we did with overlaps. But it's a complete characterization of these quantities, right? Which is given just in terms of relational quantities. So it's interesting to look at those and how can they be incorporated into a picture of classicality, right? Of the type that I'm sketching here. This is what I wanted to tell you today, but I'm open to questions. Thank you for your attention.
Well, thank you very much, Ernesto.